Hello, welcome everybody to another session of Lógicos in Quarentena. On behalf of the Brazilian Logic Society, the Logic Interest Group of the Brazilian Computer Society, I'd like to thank very much Angeline Aguinaldo, who kindly accepted our invitation to give this talk. Angeline, thank you very much.
Thanks, Bruno, for inviting me to speak here. So I'll be giving a talk about my experience getting into the field of category theory. And this is not meant to be a very mathematical talk. It's more of an experience talk. And I'm going to share some ideas about how we can apply category theory concepts to various engineering applications. So as I said, I'm going to go through a little bit about my background so that you get a sense of the perspective that I'm coming at when approaching category theory. I'll talk a little bit about my reflections on learning the concepts that are available in the theory. I'll determine, or I'll show some relationships to engineering problems, discuss some applications that I've been working on, provide some ideas on how we can improve applied category theory outreach for engineers. And then we can end the talk. Okay, so I wanted to start off about me. My background is in biomedical engineering. I have a bachelor's in biomedical engineering and a master's in electrical engineering from Drexel University. And what you're seeing on the screen is an example from my master's research, which was an image processing tool that we had developed in MATLAB in order to track cells and cell proliferation, specifically for T cells. And so we marked these cells with fluorescence and tracked those markers throughout time, and then also implemented tracking algorithms in order to see when cells begin to mitose and proliferate. And the intention of this work was to observe the patterns that were taken by these cells to see if there's a predictive way to determine whether a cell or a single line of cell has a propensity towards metastasis or cancer. So after that, I finished my degree at Drexel University, and then I got hired at the Johns Hopkins University Applied Physics Lab. I'm a software engineer project lead, and I worked on some projects with a variety of different domain applications. So one of which is developing software capabilities that process image data, specifically satellite and overhead imagery, in order to assess building damage that was sustained due to disaster events. So our stakeholders in that project are the Army National Guard and FEMA. And then another project that I wanted to highlight was a tool developed for metagenomic evaluation, tool evaluation. So in the case of metagenomic analysis, these samples are taken from environmental samples or from the dirt, from the grass, and then you have an idea about the organism profile that you should expect from that sample. And so you want to deploy the appropriate metagenomic analysis tool that will tell you what percent of organisms are present within that sample. Now, the issue is there's a lot of variety in terms of what kind of tools you can use to do this classification. Many universities and organizations are developing their own novel methods in order to classify these organisms in the sample. But there's no way to there's no way to compare the analysis between them, check if one is better than the other, more suitable for a particular use case. And this is particularly important if you wanted to forward deploy these tools in form factors that were a lot smaller than a normal enterprise server or a laptop or a cell phone. So in order to do that, this tool is developed to run these classifiers and run some genomic analysis. And then I highlighted a little bit about the tooling that I'm familiar with. So in addition to my experience at the Johns Hopkins Applied Physics Lab, I'm also a PhD student at the University of Maryland, College Park in the Computer Science Department. And I'll talk a little bit about my research interests later in the talk. But I am coming at this as a third-year PhD student and also an engineer with experiential experience. Okay, so what might be coming to mind as you were listening to that first part was that I talk a lot about engineering and some specifically software engineering applications and image processing. So the question might come about is, how did you even get to category theory? And it's a fun story because I was actually talking to my advisor about some of my ideas, where when I was developing all of these tools with a variety of applications, I found myself reusing a lot of templates that I was considering, and maybe not explicit code templates that I have explicitly made into reusable software stacks, but general ideas that I found to be applicable to both software engineering or software infrastructure for image-based deep learning versus metagenomic classification versus cyber network analysis or social media analysis. So for all of these domains, there's a lot of very common phases in which we have to implement the analysis for. So I was talking with my advisor, and I said, I want to be able to say something about how similar these systems are, even despite the fact that their implementations may differ slightly, or they're across different applications. There seems to me that there is some commonality between there's some equivalence of these systems at a particular level. So this is just some examples of the initial whiteboard process. These are not my particular doodles or drawings about the design process, but the idea is that if it's me and my team developing a solution, we often go to this whiteboard and draw out our system and notice that there's what are the major macro phases that we need to implement, and how should the data flow between them. And so we're all capturing this in this kind of informal way. And so what I found was, when I realized that when I was talking with my advisor, I was asking a very mathematical question, which is not normally the intent of an engineering student or an engineer, which is that we've started out with this behavioral or conceptual model about the design that we want to pursue. And in engineering, what we seek out is to develop an implementation of that particular model. And so every time we come up with an idea, the whole objective of engineering is to implement it and come up with a specific instance of that model. Whereas in mathematics, the idea is to generalize above these behaviors and find abstractions in which we can say some interesting properties about them and generalize over these conceptual models. So, when I was giving this or talking with my advisor, he had suggested that it sounds like I'm interested in the problems of interoperability and modularity and seeing how systems and making some characterizations about systems. So you might want to look at category theory. And so that's how I kind of ended up searching, entering the field or being pushed into the field through that recommendation. Okay, so the question then becomes, given that I have I have an engineering background, but I have no experience in abstract mathematics or theoretical mathematics. My degrees are not in mathematics, nor have I taken coursework prior to my PhD around mathematics. So the question becomes, how has it been? So how has the journey been going into this notably abstract field coming from an engineer? So as I was saying, my advisor kind of directed me towards this theory or category theory. And so naturally, I left that meeting and looked up category theory on Google because I didn't know anything about it. And I stumbled across the resource called NLab. Well, I didn't really stumble upon it. It was like the first resource that came up on Google. And NLab is a really fantastic resource for documenting new results in the field. However, it is more of an archive and note-taking platform, and I think it's provided really good. It provides a very good reference for this sort of archival and dictionary style resource. But for someone who is coming into the field, it's a little bit it was definitely intimidating to see it at first, especially given the fact that the symbols were unfamiliar to me, and that's definitely not the fault of NLab, it's more of my experience. But this being the first resource, it was very intimidating. I started asking the question to myself whether or not this was an appropriate field for me to be in, because I don't know many of the foreign symbols and characters here, or I didn't at the time. Okay, so I stumbled across this, but then I was a little more persistent to see what other resources are out there. And then the two resources that I came about were Bartosz Maluski's YouTube channel about category theory and programming, and Tyden Bradley's Mathema blog. And there's a lot of other resources that develop intuition about category theory. But the draw for these two particular sources was the fact that, at least in Bartosz's case, he was very empathetic to the programming experience. He tailored this to programmers, so it was a lot easier for him to communicate to me what the intended value of the ideas were in the case of programming. And in the case of the Mathema blog, Tyden Bradley does a really great job of exposing these concepts in beautiful illustrations. And so these are the two resources that helped me develop intuition and didn't discourage me from pursuing it further. Okay, so after I had taken a look at those resources, I felt like I had a good understanding of the basic foundations of categories and the definition. And so I was directed to by my advisor to Spencer Brainer and Esran Subramanian from NIST to talk about to figure out ways that I can facilitate the use of category theory in applications that I cared about. So one day, Spencer and Esran Subramanian were at the University of Maryland, College Park with me. We were having a meeting, and we were trying to discuss a problem of composing robotic programs. So a robot program may contain many skills that we want a particular manipulator to be able to execute. And those skills may be opening a door, putting an object in a cabinet and closing the door. And those things we suspect are inherently composable. They have expectations with those processes that you need to be able to satisfy when trying to run or execute code. And so as we were discussing this problem, Spencer mentioned this tool called string diagrams, which are the graphical syntax for symmetric monoidal categories. And the string diagrams give you this illustration of these monoidal arrows that can be composed together. And you're able to kind of track the data that is being passed and also that is occurring in parallel to a particular process. And so he was very excited about this tool. And admittedly, I was a little bit confused, given that I wasn't so familiar with the idea of formalizing pictures. So when he started drawing the pictures of the robotic programs being decomposed into processes with all these arrows and resources, where these strings being chained together, I was thinking that these are just normal pictures that I draw normally in my data flow analysis or understanding systems. And then he also described this property, which allows you to do deformation invariance and say that the boxes can slide past each other, which is again very cool and exciting. But in my mind, I was thinking that, yeah, you can redraw the picture with the boxes in different orders, and it wouldn't really make a difference. But anyway, so I spent a little more time. I left that meeting, spent a little more time trying to understand what was the excitement around this. And I realized that this was, I realized later that this was a formalization of these pictures, that you can make these pictures computable and encode them in formal structures, and you can then pass them around, which I thought was really eye-opening to me, the fact that there's this opportunity to formalize these diagrams. And so with that, I also stumbled across other resources. This one is Paolo Sabinski's Graphical Linear Algebra blog, and he does a great job of illustrating the compositions in horizontal and serial compositions and how they can be used to represent linear algebra expressions. Okay, so after that, I was getting pretty confident. Maybe it was a false confidence, but I was getting confident in the fact that I could do these formalizations of pictures, and I started to look for what other structures are available that can encode processes that I don't normally think about as having formal structure. And so these three resources here are just some of the textbooks that I've been using to develop intuition. The first of which is the Applied Category Theory 7 Sketches in Compositionality by Brendan Fong and David Spivak. The second is The Conceptual Mathematics by Lauvier, and Categories and Computer Science from Walters. And so from this, I was very excited to be able to be able to look at all the possible menu of structures that I can apply to a variety of different problems. Okay, so then I was excited to see, well, how have other people used this before? And so these are just 3 applications that I encountered that I thought were probably the most compelling for engineers. So as I share this knowledge with other engineers in my field, these are the resources that I typically point to because of their impact in helping streamline the process of engineering design or data transfer. So on the left is an example from Uber. They have a Dragon platform that they're using to integrate different data schemas together, leveraging category theoretic structures or mappings. And in the middle is a graphical syntax for dynamical systems. So if you have a dynamical system expression, and you have the graphical syntax to represent that equation in these pictures is extremely more intuitive and also can express properties in an easier way. And then the last example is the mathematical theory of co-design, which is providing system design templates around particular engineering design problems. And so being able to encode these templates in formal structures while still maintaining information about the constraints that are applied by each of the subcomponents is also extremely valuable for engineering problems. Okay, so provided all that, the journey that I'd gone on and I'm currently on, the next question probably is, what do you think about it? Do you like it? Do you not like it? How are you finding category theory? And so I wanted to highlight some benefits and challenges to it. So the benefits I found is its ability to organize my thoughts. So it's clear to me that as I get exposed to more structures and more examples of applications, that the intent of this is to formalize ideas that I have been kind of taking for granted in terms of in my head. If I'm applying a transformation from FinSet to graph, for example, and I say I have a graph and I want to index a node in that graph, that is a kind of a cognitive process that's happening in my head, but there is in fact a way to record the fact that I've exercised that transformation between these two categories. The second benefit is the graphical syntax. That's probably the most appealing, upfront appealing piece for an engineer, and that if you have a graphical syntax that is especially familiar to engineers and scientists, and you say that there is a formality to this picture, then that's very compelling, and people will want to draw more pictures and see how those pictures relate to these formal structures. And then the third benefit is the notion that functors essentially encode this idea, or this kind of sci-fi idea of parallel universes. So the way that I come to understand a lot of these topics is envisioning the fact that these categories are kind of universes with things that happen inside them. And if you change something in one universe, you can guarantee that if you, with an appropriate functor, that in the second universe, the expected behavior will happen. So if you're applying a bunch of transformations in one category, the corresponding transformations in another category will hold. And that is pretty fascinating to me. At least it's a lot of, it helped me, or it helps me develop the intuition around the value of formalizing these maps. Okay, so the challenges are that I find it a little bit hard to intuit. So it's in the same way that the organization is intended to capture my thought processes that are kind of happening automatically. It's very difficult to kind of pull yourself out of that natural state and try to really identify what are the transformations that I'm executing, and why is it and why is it that way, and how are these different representations of the same concepts being related to one another. So it's a little bit challenging, especially when you get into higher abstraction levels and higher dimensional categories. It's harder to tell whether or not you're doing things, you're kind of getting it or not. Okay, so the second challenge is that I find it a little bit difficult to communicate it without special terminology or special words. And I know that this is a challenge of many fields. The intention of naming things is to make it easier to communicate within that field. So I don't think that this is a challenge that is unique to category theory. However, when I'm attempting to explain it, the words definitely have are loaded with a lot of properties that I need to go through the steps of enumerating. And oftentimes, if I'm just getting used to or getting introduced to a new structure, nothing in the name indicates the properties that it holds. So, and that's the same with many structures, but just a way to better understand what those properties and how they correspond to the names is useful. And so that's kind of where the NLab archive addresses that challenge. And then the third challenge is that I find that it's a little bit hard to get it right, especially with real world applications. And this is coming from the point of view of me attempting to categorify real life occurring, or real occurring things occurring in the real world. And if I go to a mentor or a mentor who's a category theorist, I provide a proposition that I think that these are symmetric binodal categories or Cartesian closed categories, and is this the functor between these two, and is this functor left adjoint? Like I'm giving some propositions to them, and then they kind of look at me and say, well, yes, but I think there's other things that are better, and I don't know if that's quite right. It's not really a functor, or this is actually two categories. So I find that I may be not. It's definitely not easy to see the solution, the categorical solution, right away. Okay, so then the question comes with all of this learning is to describe what have I learned and what can I distill it down to. So the way that I attempt to understand these concepts in category theory is trying to classify results that I see in papers. And so this is my classification of results that I've observed through papers, but they may not be very precise or precise enough to your liking, or they may be slightly not correct. So you're welcome to tell me if you feel like there's a better classification. And another thing is that this class of things, these 5 classes that I've come up with, are not fully exhaustive. I don't know the whole all the literature that's available and what kind of results there are, but these are the ones that kind of stuck out to me, given that I'm looking for ways to apply these these constructions. Okay, so the first result is defining a new composition operator. So I feel that something that I've noticed is that in papers that that come out, that if there's a new construction, it often is that it may be exposing, not often, but it may be exposing a new definition on how to compose things. And so the example I have here is an operad, and the operad, from my perspective, encodes this recursive or nesting composition, as opposed to the serial or vertical vertical or horizontal composition that I was used to in string diagrams. Another type of result is to show this thing is equal to another thing, and so this is more of an algebraic. Can extend to more other algebraic structures, but in category theory, there may be an interest, or there's an interest sometimes to show that things are equal to other things, like categories are equal to other categories, or this is just a different version of a category with some additional additional structure. So the third result that I'm seeing is that to show the categorical representation has existing algorithm, or categorical representation of an existing algorithm has benefits, as opposed to a non-categorical version of that algorithm. And so the example, and I'll discuss this a little more, but the example that I'm thinking about is in the case of decorated cospans, decorated cospans give you the opportunity to decide how you want to join or how you want to compose combinatorial structures. This opportunity, or this flexibility to be able to decide how to join things instead of just choosing one way to join them, is really helpful when when applying an algorithm to it, to say that in the case of graphs, if there's connectivity between graphs, and I've chosen a very specific way of how to join two graphs, then I know for a fact that if there's connectivity between two nodes in that graph, that they will they'll pass through this particular set of nodes. And I'll talk about that in a little bit. But I think that there are some results that are tailored to showing that the categorical representation has superior benefits. Another result is just to define new graphical syntax. There's as more structures are defined, the need for how to express that in the graphical syntax is also accompanying that new result. And so the example here is string diagrams, and then the addition of more bells and whistles, as they say, to add to string diagrams is part of the result. Okay, and so the last example, or the last result that I'm seeing, is that is the desire to show that things are analogous to other things. So this is the use of the natural transformation and the functors, from what I can tell, and there's this desire to make some claims about how close or how similar things are to other things. Okay, so I just gave you a list of some results that classes of results that I felt were emerging. So how does this relate to engineering? Okay, so I've enumerated some examples of engineering problems that we are often encountering when pursuing a design. There are 5 engineering problems that I've listed. So the first of which is the security and safety, otherwise termed as, I'm terming it as verification. And what falls under this is the question of, did I build the product right? So can I make some guarantees about whether this code will compile, or whether there's no bugs in this code for a given input? Can I make claims about that? And verify that I built it correctly. Another engineering problem is effectiveness, and also termed as the validation. So did I build the right product, and how do I measure the fact that I have built the right product, and how do I demonstrate that to the customer? Another problem is efficiency. So can I make this code run faster or with fewer computations, with a smaller memory footprint? So all of these are things to consider when trying to develop tools. How efficiently can this particular system or process run? The third problem is comprehensibility. Can I understand what this product is doing? So someone who is using the tool or the product, how well can they understand the nuances of the process that it is executing? And how do we communicate that to someone who's using it? And then the last problem, which is not so much of a problem, but more of a business motivation, which is innovation. So how can I push the boundaries of the tools so that I can compete in the market, or have some novel contribution to society? Okay, so so these results, if you kind of squint a little, you can align them to the ideas of the categorical results, or the category theory classification of results, and start saying, like, how can we start using these types of results in some way to address a small part of the engineering problem. Okay, so then the question becomes, given all of these things, how can I apply it in my work? So I've just included some example applications that I'll go over very briefly to show that there is some alignment, or some attempt at alignment towards these engineering problems. Okay, so before I go through the applications, I just wanted to describe for you a framework that I'm noticing as I go through these different applications and trying them out. And there seems to be 3 steps in this process of integrating engineers and category theorists. And I think the order of the first 2 is debatable, but at least one of the steps is to decide on the category theory tools. So I think it may be that you have to first align the application concepts first. So 1 and 2 are a little bit of the category theory and category theorist and the engineer having a dialogue about what is the application, explain to me what the concepts are, and then the category theorist decides on the tools that make the most sense for that application. And then it's a kind of an iterative process. So you keep deciding on, or better refining the structures, and maybe defining new structures that will be better suited for modeling that concept. And then after those things have been hashed out, then it's about encoding the model. So how do we implement the concepts that we now have either defined or decided on based on our domain? And how do we encode it so we're actually leveraging the properties that are afforded by the category theoretic structure? So one example of encoding the model is the CatLab library in Julia, which is developed by Evan Patterson and James Fairbanks, that is using these implementing many of these structures in a Julia framework so that they can be leveraged for modeling different concepts. Okay. So I'm going to go through a few examples, as I said, the first of which is this idea of goal-oriented robot programming. I alluded to this earlier with the string diagrams, but the question is, can we model robotic programming in this compositional way so that we can more easily create modules or reusable skills for a given robotic arm, regardless of brand or manufacturer or software development framework. So how do we encode the mappings that are relating skills to specific SDK syntax in order to improve modularity? and be able to run this in a variety of environments. The second example that is kind of in the works is this idea of modeling low-level software in reverse engineering to in a categorical way, so that we can relate the high-level software abstractions, but also connect high-level software abstractions to low-level software abstractions, but also see if we can compose the opcode that's present within low-level software to witness vulnerabilities or bugs or issues that might happen when attempting to compose these operations together. And this is joint work with Georgios Spakourtzis, Spencer Brainer, and Esron Subramanian. Okay, so the other example that I've worked on is the use of decorated cospans to improve to measure connectivity within a network. So I mentioned that a decorated cospans can give you the opportunity to choose how to join different combinatorial structures together. So if I have two graphs and I want to join only on a single node, despite the fact that these disjoint networks may have other shared nodes, I just want to have the ability to choose which nodes I want to connect over. And so the decorated cospan construction lets you do that. And so when you join these two graphs over that node, if I had a question about whether this blue IP address, which is just a machine on some network, is connected to an IP address on another network, which is the yellow one, if I can say, using a connective component algorithm, whether or not those are connected, I know for a fact that it's connected via the node that it was joined across. Okay, so this other example is this is the second to last example, but this example it addresses the comprehensibility that I was referring to. So in the case of domain-specific languages used for AI task planning, we often are faced with a solution to an AI based on an AI solver that is pretty opaque. There is just single lines of actions and their and values that will be substituted into their variables. And so when someone is attempting to debug or understand the reason for a solution in AI planning, they have to look at the solution compared against the description of those actions in the domain file, and then kind of trace all of the effects through in that way. But I think that this can be expressed in a composition of symmetric monodal category arrows. So this, you can see that this is a chain of actions: pickup, stack, pickup, and stack. And the benefit of having this structure is that you also have knowledge of what literals, which are the strings that are available while running one of the actions. And you can also see by this representation, this graphical representation, what literals are actually being used and where are they being used in the process. Okay. Okay, so the last example that I have to discuss is this innovation piece. So one of the motivators of using category theory in general is to use solutions from one domain to move another domain forward. And so the question is, can we use the same philosophy in order to move a domain such as robot programming forward based on the way that we understand programming languages and compiler theory? So the problems with the robotic programming is you often have to program these robotic manipulators in their low-level languages. You have to describe their waypoints and say how and the angles in which your joints, you should actuate the joints. But that level is not very accessible to many machinists. So they have to hire offline programmers to figure out what's the right program to run these manipulators. But there's still ongoing work to develop abstractions that are more appropriate for robotic programming, so then we can reach the application level of programming robots. And so given that programming languages and compiler theory has made a lot of headway in making these high-level languages, can we use similar ideas or concepts or structures to encode abstractions within robotic programming? Okay, so that's the end of the examples that I wanted to discuss, and then we're almost wrapped up here. I just wanted to provide some idea of how we can improve applied category theory outreach for engineers. So one of the ideas is just describe what aspects of the problem help you decide on the tools. I think it's pretty, and what I mean by that is if we are applying a particular construction to address a problem, just making sure that what aspect of that problem is in fact amenable to that category theoretic construction, and like what is the rationale behind that. I think since this is such a new area of research applying category theory, I think this is more of a prospective suggestion. Okay, so another idea is categorifying existing engineering abstractions. So there's a lot of tooling out there around system modeling, in general programming, high level and low level. So is there a way to categorify these existing tools and demonstrate the benefits of the representations there? Another idea is the use of cognitive versus categorical translation tables. So as I was saying earlier, the benefit that I'm seeing is the ability to formalize an abstract idea that I have in my head about how transformations are occurring. So in this example, this was the decorated kill spans for network security example. There's an alignment between some cognitive process that I'm thinking about and the categorical process, the categorical concepts that are being used to translate that cognitive process. And then the last thing is to visualize the taxonomy of categories to show how they generalize or restrict relative to one another. And this came about when looking through NLab and trying to find definitions of different categorical structures. And I had not known, or I often don't realize how that structure may relate to another structure, whether it be through an addition of a property or a generalization of this category. So some sort of map, maybe like this one, or a tree structure of how categories relate to one another in order to help someone navigate the definitions and explain why these or explain how these categories are related. Okay, so that's the end of the talk. Thank you for listening. I'm happy to answer any questions.
Thank you very much, Angeline.
Mm-hmm.
So as usual, I'll have some time for comments or questions. Just a curiosity, I do really agree with you that graphical notation is a really nice thing. How was your experience to get from this graphical notation to programming language code?
So I think the fact that I can, so if I'm attempting to implement these structures in code to correspond to a graphical syntax, I think having the graphical syntax help me decide what components I need to be encoding in my library. So if I have a library that is encoding a symmetric monodal category, the fact that I have this picture to reference to say that if I'm encoding it correctly, the composition of them should show that there is a tensor product of these identity morphisms with the with some other morphism based on this picture, I kind of use it as like a verification of the fact of implementing the structure.
But do you know about anything that automated this, some parts at least of the translation?
Automating the translation, no. I think it. If I understand your question, I think the best way to relate the implementation to the graphical syntax is if the library implements, when the library is implementing the structure, to also implement the interpretation of in the graphical syntax.
I think I have seen something from monads to Haskell, but I'm not really sure.
Oh, okay, so, great.
So Valeria?
Hi, Angeline. Yeah, it's very, I mean, it's very nice to hear your perspective on that. You know, I kind of, I was kind of a little bit worried that some of our audience might feel alienated because, you know, some of the logicians are not so keen on software engineering, but I think, you know, I think this kind of, your slide 29 shows fairly well kind of that, you know, AI and planning are part of that, and there's kind of other things that yeah, kind of, right. So this is just kind of a subset of first order logic that we are looking at as a bit of category theory. So that's kind of quite cool, and there's much more from where that comes from, right? Mm-hmm. There's, you know, doesn't have to be in planning, doesn't have to be in AI. There is an awful lot of logic as logic within programming. So kind of your other picture that has all the symbols of Java and stuff like that. There is also kind of, there's lots of logic implicit in there. I actually, the only thing I actually disagree a little bit is this business that you guys seem to be so keen on. So, you know, I should just shut up perhaps. But I think, to my mind, the graphical syntax helps you think about it, but it doesn't help so much when it comes to implementation, because, you know, at least the way I think about it, you have to kind of go back to X and Y's and kind of big structures and stuff like that. So, I don't know. I wonder.
No, yeah, no, I see what you're saying. So I guess you're disagreeing with the fact that the diagrams are, or we're rooting our design in the diagrams.
Yeah, I think I am disagreeing on that one.
Yeah.
I think that the diagrams are really nice, especially when you talk about the communication.
Mm-hmm.
Yeah, no.
Not to all of the
when it talks about the communication, they are brilliant, right?
Mm-hmm.
It's on the implementation that I have a problem.
Yeah, no, you're definitely right, Valeria. The diagrams are mostly entirely communication oriented. They're and even that the communication to the team is not perfect given a look of a picture. What would be ideal is if you took that picture and it was encoded somewhere, and then it generated code for you or some sort of template for you that that is a result of that. I think that would be more. It would make those diagrams a lot more useful. Yeah. So I see what you're saying, Valeria. It's not. Yeah, we're definitely not claiming that the design is strongly connected to the picture.
Well, I have to say that all your examples seem really exciting to me, at least. You know, they're great. So I hope you're going to give us your slides so that we can check the 5 different papers and stuff.
Mm-hmm. Yeah, I can share these with you.
I missed the beginning of the talk, so maybe I question that I have but doesn't make sense in the context of your presentation. But the perspective that the Haskell community have is a little bit different on using category theory to model the libraries, right? So many of the libraries are constructed in a way to follow the concepts, not only concepts from category theory, but also respect the laws imposed by the categories, right? Specific categories. And I wonder if you talk about this in the beginning, or if you have anything, because it's a difference in the perspective that you guys were discussing, right? So one thing is you use that as an artifact for communication, and eventually you want to concretely transform into concrete code. Is it possible or not, or does it make sense or not? This is the discussion that you guys are having. But another perspective is to guide the implementation, because you are following you are following in respecting the algebraic laws that the category 3 force you to think in a more structural and mathematical way during your code development.
Mm-hmm. No, so yeah, I didn't cover that, any thoughts around that in the beginning, but I think that that's right. You could, or yeah, it would be a desirable effect to be, if someone understands the structures well enough, to start guiding, embedding it or baking it into the implementation and basic design patterns. I think that would be extremely beneficial if we were able to educate a lot of programmers to be able to code in that way. Yeah, because then you can start leveraging more of the properties.
Simple things, right? For example, many libraries implement a lot of different functions, but the concepts around the library are not well defined. So the functions are not composable at all, and doesn't make any clear statement about what are the types that are involved in what's the problem that you're trying to solve, what are the kind of objects that you're supposed to deal with, and how those functions should compose and should inverse one with each other, and how so those laws are guiding people to develop better libraries, right? And that's a very interesting perspective. But thank you for answering. Sorry for missing the beginning. I have to make this question. So
no, that's okay.
Well, you did say something about that, Angeline. You kind of go back to the slide that have the 5 things side by side, kind of. Yeah, I mean, didn't you say something about categorifying software? I think I saw somewhere categorifying the software engineering kind of concepts.
I think maybe it was in. Well,
yeah, categorifying existing engineering abstractions, right?
Mm-hmm.
So this is kind of hard, right? Because I don't think the engineering abstractions are that consensual, there's kind of,
yeah.
But it's pretty good. I like it. Might as well go for the killing, just go for the top prize, but it is hard, right?
Yeah, no, that's right. I think, right, if you're not keeping in mind making things consistent when implementing these tools, like algebraically consistent, then it's hard to shoehorn a structure in there. But maybe maybe it's possible. It would be very helpful if we were able to categorify these things.
One more thing. Sorry. One more thing. I think I don't like very much your map of mathematics.
Okay.
There's another map of mathematics that I like much better. That's called the Math Stunt. Also comes from the YouTube. I can send it to you at some stage. And that one has category theory kind of the one that I'm thinking of has category theory very prominently.
Oh, I think I've seen that before. It's like a landscape.
That's right. It's called the Math Stunt.
Okay, yes, I think I've seen that before. No, that's right. Yeah, category theory is on this really small.
I don't like this one very much because I think it's exactly not kind of organizing the taxonomy so clearly as the other one. But the other one Oh yes, there is. Yes, Karina, the moon of category theory, correct. I mean, that's the second version. Someone changed it because originally category theory was a shore, a beach, which I liked it, and then someone made it the moon, right? But you see, I think the problem is that this one does not give avenues of understanding, whereas the other one is a little bit more poetic, but it does have.
No, yeah, that's right. Yeah. So if we can make something of just categories that is a map or more poetic than this, then I think that would be super helpful.
Yeah, don't pay any attention. I'm just kind of joking.
So any other question or comments? Okay, so thank you very much again, Angeline. Really nice talk.
Thanks for having me.